Hello everyone, today we're gonna solve some classical mechanics problems. Let's just get straight into it. Mostly, we will be solving the problems that test our understanding of uniform circular motion. So you just need to know a few basic formulas. You need to know that centripetal acceleration is velocity squared over the radius of the circle. You also need to know what is the centripetal force, but we're not going to cover all of it right now. If you are completely unfamiliar with what these two mean, please go ahead and watch my last video, and there I fully introduce you to these amazing concepts in physics. So let's tackle the problems then. A 10-kilogram mass is attached to a string that has a breaking strength of 200 newtons. If the mass is whirled in a horizontal circle of radius 80 centimeters, what's the maximum speed it can have? Assume the string is horizontal. First, let's just draw what's going on here. Just a quick picture so that we understand what we're even dealing with. Here we have a mass, it is 10 kilograms, is attached to a string that has a breaking strength of 200 newtons. Let's say the breaking strength is Ft. It's going to be 200 newtons. If the mass is whirled in a horizontal circle, so it must be that kind of circle. Wait, let me just get it out of here. Oh gosh. Anyway, say that is our circle. That is not a perfect circle. I am sorry. Ah, gosh. Let me do that. That's going to be our circle. That's going to be our circle. So the strength that would break the circle is 200 newtons. Then we also know that if the mass is whirled in a horizontal circle, that's our circle of radius 80 centimeters. Please always convert your units to kmcs, which basically means kilograms, meters, and seconds. Never deal with centimeters. 80 centimeters is the same thing as 0.8 meters, so we're going to write it down. What maximum speed can it have? We have a mass right there, it's 10 kilograms. What maximum speed, the speed is the absolute value of velocity, can it have? Assume the string is horizontal. Alright, so how do we figure it out? Look, in our centripetal acceleration equation, we have the velocity squared over r. So if we know the acceleration, we'll be able to figure out the velocity, which also is going to be the speed in this specific scenario. Since we know the variable r, which is the radius, it's 0.8 meters, we'll be able to figure out v if we know a. How can we know acceleration? So acceleration is always acting toward the center of the circle, centripetal acceleration. That's why it's called centripetal. It's pointing toward the center of the circle. Well, we know that centripetal force is actually equal to mass times the centripetal acceleration. It comes straight out of Newton's second law. The net force is equal to ma. What is the centripetal force here? Well, we've been told that the breaking strength of the string is 200 newtons. So if our centripetal force is greater than 200 newtons, then this string is gonna break, and the whole problem is no longer valid. It's just irrelevant. So our centripetal force needs to be either equal to or less than the breaking strength of the string. Let's make it equal to so that we get the maximum speed. We're asked maximum speed. So if we make it equal, we're going to get our maximum possible acceleration, which means we're going to get maximum possible velocity. Now it's just plug and play. So the centripetal force has to be equal to 200 newtons, which is equal to MA right there. We know M is 10 kilograms times centripetal acceleration. So centripetal acceleration should be 20 meters per second squared. Now we know the acceleration. Can we figure out the velocity? Of course we can. Let's get it over here. We have the centripetal acceleration is velocity squared over the radius. We know the centripetal acceleration is 20 meters per second. We're solving for v squared, for v to be precise, and the radius is 0.8. So 0.8 times 20 is going to get us 16. So velocity squared is 16. So velocity is either positive or negative 4 meters per second. But we know that we're talking about speed. Speed cannot be negative. Speed is a scalar constant. It doesn't have the negative axis. So our final answer is going to be 4 meters per second. That is the maximum speed that this object on the string can reach without the string breaking in the process. Let's move on to the next question. This one is pretty interesting. Buckle up, it's going to be pretty tough. So a roller coaster car enters the circular loop portion of the right. Let's imagine it. There we have the circular loop, and we have a roller coaster car. But where is it exactly? We don't know whether it's at the top, at the bottom. So let's read further. At the very top of the circle, where the people in the car are upside down, allegedly, the speed of the car is 25 meters per second and the acceleration points straight down. So if the roller coaster car is at the top of this circle, then the speed of the car, which again is the absolute value of velocity, is 25 meters per second. And the acceleration points straight down. Yeah, that makes sense. As we discussed earlier, centripetal acceleration always points to the center of the circle. If the diameter of the loop is 50 meters, the diameter we know is like this whole thing. Diameter is radius times 2, so the radius is 25 if the diameter is 50. Let me put it right over there. So radius is 25 meters, and the total mass of the car plus passengers is 1,200 kilograms. Alright, 1,200 kilograms. Mass is 1,200 kilograms. Find the normal force exerted by the track on the car at this point. We know that the normal force... Oh, I can zoom in here. No, I can't. Basically, normal force here is going to point downward. We know that if there is a human standing on the ground, the normal force will push the human up, while the force of gravity will pull the human down. In this specific scenario, we have everything upside down. There we have a car. So normal force is going to be there. It's basically the force that the surface exerts on the object that rests on that surface. So normal force is going to be here. I'm going to name it F sub n. And we need to figure out F sub n. That's what we're solving for. But let's read until the very end. Also, find the normal force exerted by the truck on the car when it's at the bottom of the loop. So we have the situation where the car is at the bottom as well. We also need to figure out the normal force in this scenario. Assume it's still traveling 25 meters per second at that location as well. So here, the absolute value of velocity is still 25 meters per second. Now let's draw the free body diagram so we can understand how the normal force relates to all other forces. Well, actually, there's only one force here, the force of gravity, other than the normal force. So let me say this is at the top, this is at the, how can I get rid of it? Oh gosh. At the bottom, and we're gonna draw two separate free body diagrams for two situations. When the car is at the top, we always have the force of gravity, so let's call it mg. We actually know what the force of gravity is. We know in the mass is 1200 kilograms, and assuming that the object is on Earth, which in most classical mechanics problems is the case, then we can say that g is about 10 meters per second squared. Then we have normal force, as we discussed. No force is upward, note that. Then in this situation, we have normal force upward, because now the surface is at the bottom of the car, not on top of the car. And mg is always acting on any object on Earth or near any astronomical bodies for that matter. Alright, how do we figure out Fn from this thing? First of all, let's define the axis. Let's say this is positive y-axis, meaning that part is going to be negative y-axis. We're not going to deal with x-axis here because there are really no forces in that direction, so it would be just useless. So let's write all glorious F equals ma. So what's the net force when the car is at the top? We know that we have the force of gravity, mg, plus the normal force is equal to the mass of the object, which is 1200, and the centripetal acceleration, which we also need to find. That's going to be easy. We have the radius, we have the speed, so that's easy peasy. So mg, what is mg? M is 1200, g is 10. So we get 1200 here. Oh no, 12,000, sorry. Plus F normal, which is what we're solving for. Then the mass is again 1200. Then the centripetal acceleration, let me do it here. Velocity squared over the radius. Velocity is 25. That is squared over 25. Gives us exactly 25 meters per second squared. So here times 25. So the normal force is equal to, let me do it real quick. 25 times 1200. That gives us 30,000. So the normal force is 18,000 at the top. What's the normal force at the bottom? Here we have a free body diagram for the bottom situation. Let's do the same thing, but now note that the gravity will act in the positive direction and the normal force will act in the negative direction. So we can say mg minus the normal force is equal to ma. Here we found that ma is just 30,000 because 1200 times 25 gives 30,000. And mg is 12,000. So here we have 12,000 minus F normal equals 30,000. If we get F to that side and 30,000 to that side, we get F normal is equal to 42,000 newtons. This is at the bottom. So these are our solutions. And I want you to notice that it actually makes a lot of sense. The reason why the normal force is different is because the normal force is electrostatic force. They're basically some atoms interacting at a micro scale, but we're not going to dive into electromagnetism behind it. I just want you to understand that when it's at the top, the gravity also acts on the object. But when it's at the bottom, the gravity still acts, but in order for the car to stay on the surface, its normal force should be higher than the same scenario, the counterpart with the top case. Those are our answers. The normal force at the top is 18,000, sorry, and the normal force at the bottom is 42,000. And now, a very interesting question. In the previous example, if the net force on the car at its topmost point is straight down, why doesn't the car fall straight down? So here, let me draw it one more time. When the car is at the top, we have the force of gravity. We have the normal force. We have acceleration in that direction. Why doesn't the car just fall down to the ground? Well, it's because its velocity is non-zero. Velocity is 25 meters per second. If the velocity were to be zero, the car would most definitely fall on the ground. I mean, try to visualize it. You are going in circles on this loop portion of your roller coaster, and if the car doesn't move at all at the top, then you would fall. But why don't you fall? Because velocity is non-zero. That keeps you moving in circular paths. And one more thing, if acceleration is less than the gravitational force, meaning if the centripetal acceleration is less than 9.8 meters per second squared, then the car wouldn't necessarily fall straight on the ground, but it would go off its circular paths. So it would go just normally, and then it could just fall right there, or right there, right there. Why? Well, if the force of gravity is greater than the centripetal acceleration, the object will have more forces acting to bring the object down than the forces to keep the object moving in its circular orbit. And one more reason why the object isn't gonna fall right here is because the acceleration, no, look, the force predicts the direction of the acceleration. That is correct, because F equals ma simply means that if F is in the negative direction, then acceleration should also be in the negative direction. Since m is just a scalar, it doesn't really play any kind of role here. Which basically means that if we have that velocity, the object wouldn't fall. It would not fall straight down. It would fall, but at an angle, since we already had the velocity here at the top. I hope it makes sense. If it doesn't, please leave a message in the comment section, and I will definitely shoot another video trying to explain it in more detail. But this should make sense. If you try to really visualize it yourself, it makes sense that if velocity is non-zero, then the object should keep going, and because the centripetal acceleration in our case is 25 meters per second right there, then the object would still follow its circular paths because 25 is greater than 9.8, which is the gravitational pull of the Earth's on the object. Thank you for your time, and I hope it really helps.